Okay, and so now what I want to do is I just want to recall the definition formally now of a horizontal asymptote. Okay, and so the real definition of a horizontal asymptote involves limits. But when you were first introduced to this in pre-calculus, we weren't going to use limits, all right, because you didn't know what a limit was. And so you might remember that there were some horizontal asymptote rules that had to do with the degree of the numerator and the denominator and so forth. And so you knew that if the degree of the denominator was bigger than the degree of the numerator, that the horizontal asymptote was y equals 0. If the degrees were the same, then it was the ratio of the leading coefficients that gave you the horizontal asymptote. And then if the degree in the numerator was bigger than the degree in the denominator, you knew that there was no horizontal asymptote, right? So those were the, three different cases that you had for in terms of trying to figure out the horizontal asymptote of a rational function. And so now you are going to actually see where these rules and air quotes came from, all right? Where they came from is calculus. So we kind of told you the results without telling you where they came from. So it's like we previewed the movie, but now you get to watch it. Okay, so here I'm saying to you that the line y equals b is a horizontal asymptote of the graph of the function f if either the limit as x approaches infinity of f of x is equal to b, or the limit as x approaches negative infinity of f of x is equal to b. And so I just want to note to you that, remember, b must be a number, okay? It's not infinity or negative infinity. Okay. So here I just want to compute this limit. And so what I'm going to do is I'm going to note to you that I want to, since I'm looking at the limit as x approaches infinity, it's all about figuring out the end behavior, all right, of what's going on in the numerator and the denominator. And so what happens as x approaches infinity to the function x minus 5? Well, you would say that x minus 5 is just a line, right? And so as x approaches infinity, we know that x minus 5 is also going to approach infinity. And so in the numerator, I have that this idea is that I have that it's infinity. In the denominator, I see that I have a quadratic function here. And so I'm going to have, because 2 is positive, I'm going to have a nice upwards looking U shape. And so as x approaches infinity, what's in my denominator is also going to approach infinity. And so what I have here is infinity over infinity. And so if you remember, we talked about how infinity over infinity is an indeterminate form, which means I don't know what the limit is. I need to do some work. I need to do some algebra. Okay, so here, what I'm going to do to figure out this limit is I'm going to divide by the highest degree in the denominator. All right, so that's the algebraic idea to try to figure out these types of limits. So I'll divide top and bottom by the highest degree in the denominator. Okay, so let's do that. So the highest degree in the denominator here we see is 2, right? So the highest degree in the denominator is 2. So I'm really going to not necessarily divide by 2. I'm going to divide by x squared. Okay, so here I might say instead divide top and bottom by the term with the highest degree in the denominator. Okay, and so here I'm saying in this case divide by x squared. Okay, so I'm going to do that. I'm going to get that this is the limit as x approaches infinity of x minus 5 over x squared divided by 5 plus 2x squared all over x squared. And so now what I'm going to do is I'm going to also note to you another thing in algebra. Okay, so note, if you have a plus b over c, we know that this is equal to a over c plus b over c, right? Because usually what you have is on the right, you're trying to add these two fractions with a common denominator to get what you have on the left. But instead, we're working backwards now. We're starting with what we have on the left, and we want to end with what we have on the right. And so here, when I look at this, I'm going to say, well, this is the limit as x approaches infinity of x over x squared minus 5 over x squared all over 5 over x squared plus 2x squared over x squared. And so if I simplify here, the first part, x over x squared, I can simplify to 1 over x minus 5 over x squared this is all over 5 over x squared plus 2. Okay. And so now here's the idea. We're going to look at each piece. Okay, and then this is just 2. But what's happening as x approaches infinity? What's happening to 1 over x? Okay, well, we would say that this limit, that limit there is 0, right? Because I'm in that 1 over infinity case. Okay, because as x approaches infinity, so does x, right? So here I'm saying to you that I have that 1 over infinity approaches 0. Okay, so that's the first part. I have 0. Okay, what's happening to the limit as x approaches infinity of 5 over x squared? Well, as x approaches infinity, what's happening to x squared? X squared is also approaching infinity, and so what I'm going to have is 5 over infinity within the limit that approaches 0. Okay, so now I have 0 minus 0 over, well, I have the same thing again in the denominator, 5 over x squared. We just said that that's within the limit. I have 5 over infinity, and so that we know that that just goes to 0, and so the limit there is 0. And then plus 2. And so here I have 0 over 2, which is equal to 0. And so now I've computed this limit. So now I'm asking you, is there a horizontal asymptote line for the graph of the function f is equal to x minus 5 over 5 plus 2x squared? Okay, so basically the function that was just in the limit there. And so since the limit as x approaches infinity of my function was equal to a number, then I know that there is in fact a horizontal asymptote. So the answer is yes. And what my limit was equal to, that's going to give me my line. All right, and so the HAL for the horizontal asymptote line is y equals 0. Okay, since my limit was equal to 0, I know that the horizontal asymptote line there is y equals 0.